In the previous video, we introduced sort of our concept of waves and our mathematical model we're going to use to describe waves. Now, if you recall, a wave was a disturbance traveling through some medium at some constant speed. So our wave model for a sinusoidal wave was essentially describing the displacement, whatever that was in the medium, as a function of position and time. And it equaled a sine kx minus omega t plus phi naught, where a was some amplitude of that disturbance. So if we had, say, a wave on a string and we were shaking one end of that string, we'd see this sinusoidal sort of history graph displacement as a function of time, and the maximum displacement would be a, that amplitude. Likewise, if we plotted it as a function of position at a given instant in time, that maximum displacement is a, the amplitude. The function is sinusoidal and it depends on x and t. K is what we defined as the wave number. And it essentially captures the periodicity in space, right? We know that the displacement repeats itself in space every wavelength lambda. So we defined K as 2 pi over lambda, essentially converts a position into radians so that when we put it into that sine function, we have radians, which the argument of sine has to be, and it has the same periodicity that we need, that wavelength. Similarly, we defined the angular velocity or angular frequency omega the same way we defined it for simple harmonic motion or uniform circular motion, where it's just 2 pi times the frequency or 2 pi divided by the period t. Again, this captures the periodicity of this wave with respect to time. If we look at a single point on this string, it's going to go up and down as that wave travels through it, and it takes one period to do that. It repeats itself in time every period, capital T. So that's what that angular frequency is. This phase constant is what we call that. It's just a constant term in the argument that essentially it does the same sort of thing that that phase constant did with simple harmonic motion, in that it allows us to describe arbitrary initial conditions. Now, the other big thing we looked at when describing these waves is the velocity, the wave speed, how fast these waves are traveling through space. And we said that the wave speed was equal to the wavelength times the frequency, or written another way, the wavelength over the period. This was kind of almost our definition for the wavelength. We defined the wavelength of a wave as the distance traveled in one cycle of motion or in one period. So this ends up being just distance over time. And because we know that the frequency is related to the period in that way, we can just write it as the wave speed is equal to the wavelength times that frequency. We can write it another way too, though. If we think about how we've just defined angular frequency and our wave number k, we can see that omega divided by k ends up just being 2 pi over t divided by 2 pi over lambda. So this ends up being lambda over t, which is our wave speed. So we can write it in terms of angular frequency and wave number, or in terms of wavelength and frequency. And this is essentially how we built up our wave model in the last class, or in the last video. Now, one thing we didn't really mention is if we consider that wave on a string, we can think about how the medium versus the wave is actually moving, right? So if we have this string and there's a wave traveling on it, if the wave is moving in this direction, right, that displacement, this shape is traveling to the right. But if we look at any point on that string, it's not moving left or right, it's moving up or down, right? If you take a rope or a string and start shaking it, the string doesn't move left or right. The string moves up and down, but the shape of it, that displacement moves right. So what we have is this in these transverse waves where the displacement is actually a delta y. That displacement as a function of position and time is equal to a sine kx minus omega t plus phi naught, um, this displacement is actually, a delta y, how far these the string is at that location away from its equilibrium value. If we want to know the speed or the velocity that that's moving, well, we know that that displacement is going to be delta y, the derivative of that displacement with respect to time. How fast is this distance changing with respect to time is that speed. So we can just take the derivative of our equation here, our wave model, with respect to time to figure out what this velocity is. And what you'll see is, well, the omega comes out, so we end up with negative omega a. This sine becomes a cosine, and everything else just stays in there, plus phi naught. So we can figure out that velocity in the y direction for the velocity of the medium, how fast the string is moving, which is different than the wave speed, which we already know as lambda times frequency. So we have to be careful here with what we're trying to describe. We have the speed or the velocity of the medium is the derivative of the displacement of that medium with respect to time. The wave speed is different. That's how fast that disturbance is moving through the medium. But with that, we have a really nice description or mathematical way of describing our waves. And this is a great model because it applies to essentially all the types of waves we can think of, right? The wave on a string example, we've been using that because it's sort of familiar and easy to visualize, but this describes that perfectly. One of the things we can look at is the wave speed. If we look at the book goes through this sort of derivation in a little more detail, but it turns out wave speed is a property of the medium. So if we go back to this equation for our wave speed, the wave speed is a property of the medium. How fast that wave moves depends on what it's moving through. The frequency is actually a property of the source of that wave. So if you consider again that wave on a string example, you have let's say a small light piece of rope attached to the wall, and you start shaking it up and down with your hand. How fast that wave moves through the string depends on the properties of the string. How tight is it? How heavy is it? Whereas the frequency, how fast it goes up and down, depends on the source of that wave, i.e. you. How fast do you decide to shake it up and down? This is from the medium, and the frequency is a property of the source. So when we look at a wave traveling on a string like this, turns out the velocity of that wave, the wave speed through that string, depends, like we said, on properties of the string, and primarily just the tension in the string, T times S, divided by the mass density or the linear mass density, which is just, if I have a wire that weighs 10 grams and it's 1 meter long, that's 10 grams per meter. That's the mass density per unit length in there. And you can determine the velocity of the string, just the velocity of the wave on that string by using that equation. And with that, we know we have our displacement is equal to a sine kx minus omega t plus phi naught to describe that wave throughout the whole medium. If we know the velocity the velocity of the wave, which we get from this, we know a lot about that wave, are in a good position to describe it. We can also apply the same wave model to other types of waves, though, like sound waves, right? If you think about what is a sound wave? Well, let's say you have some speaker here. What happens when you place something on that speaker? It oscillates back and forth, right? So it's going to go back and forth. When it goes forward, it's going to push all the air in front of it kind of together, and we're going to get this dense sort of compression of air molecules in there. And then when it pulls back, there's going to be, you can't pull the molecules with it. So there's going to be what we call a rarefaction or sort of a gap or a less dense region of air or whatever you know the sound's traveling through in that region, and we can see that sound and that that density wave sort of travels through the room or whatever whatever it's traveling through. If it's in underwater, it's traveling through that fluid. Um, and we have this compression region and then a rarefaction where it's less dense, and then another compression region. And those just travel through the air. Eventually, if you're listening to it, it'll hit your ear, vibrate your eardrums. Your brain will interpret that as a sound. But these types of waves can be, described by that same displacement equation that we built up in our previous model. Um, but that's essentially all the sound waves are. It's a different type of displacement. We're displacing the sort of pressure or density in the air, um, but the wave, that displacement, is described with the same wave model we have. The speed of sound depends on the properties of the medium again. So in a typical room temperature environment with standard pressure and that, the velocity of sound is about 343 meters per second. And the frequency, well, it depends on how, whatever the source of that sound is. Humans can hear between 20 hertz and 20 kilohertz, right? And this depends, obviously, on different humans. There's variation in how well we can hear. Um, but just because humans can't necessarily hear those sound waves doesn't mean they can't exist, right? You're probably familiar that dogs can hear much higher pitched frequencies than humans can, um, and there's a bunch of different ways of detecting sound waves. But humans, essentially, the lower the frequency, the lower the pitch or note that you would hear. Those are the bass, the deep notes, and the higher the frequency are those higher pitched, treble frequencies. If you go to frequencies much higher than that or above where humans can hear them, we refer to those as ultrasonic frequencies. And those are the types of sound waves that are used in medical imaging, right? And can get these sort of ultrasounds of tissue and that. And if you think about, you can think of back to how why ultrasonic frequencies work, right? If we put some sound, we're looking at sound traveling through some medium. If we set this frequency really high, well, the medium will determine, the speed of sound in that medium. So the speed of sound in organic tissue has some value. The frequency, when it's 20 kilohertz or greater than 20 kilohertz, up in the megahertz range, that wavelength will end up being smaller and smaller and smaller. And it turns out that this wavelength relates to the precision or the detail you can see in those images. So with these ultrasonic frequencies, we essentially are throwing these waves at things we're interested in the body, watching, measuring how those waves bounce off, and the wavelength sort of limits the precision or the detail we can see in those images. So if we use ultrasonic frequencies beyond what humans can hear, we actually get more accurate and more detailed images. But again, sound waves are just another type of wave we can describe and think about with the same wave model we've been discussing. Another type of wave, light waves. So turns out light is actually just an electromagnetic wave, right? We don't cover what electric field and magnetic fields and that are in this course. That's covered in Physics 202, the next course in the sequence. But the gist is light is just a displacement in those fields. The electric magnetic fields have that amplitude or the field oscillates back and forth throughout the medium, and you have the same type of wave model we've been using. Turns out the speed of light is determined by the medium you're traveling through. And in general, if you're in vacuum, the speed of light is extremely fast. It's essentially, approximately 3 times 10 to the 8 meters per second. So the light can go around the Earth about 7.5 times in a single second, right? So if you think about it, that's why all our telecommunications, our cell phones, the speed of sound, if you remember from the last a slide or two ago was about 343 meters per second. So you can imagine trying to make a phone call even just to the other side of the city, 10 kilometers away. If you make a sound, it would have taken, let's say we're 3 kilometers away, you're taking about 3 seconds, or sorry, 10 seconds or so for that sound to travel that far. That's not going to be a very good conversation. You have to sit there and wait for it to get there. However, what our cell phones and that do is they convert that sound signal into an electric signal and then transmit it at the speed of light using these electromagnetic waves. And it can get, it can travel as far as you can, essentially instantaneously to to our human perception, and then it converts it back into in the speaker in your phone, so you hear that sound, and you can have these conversations with people even on the other side of the world with no real noticeable lag. And it has to do with just the fact that those electromagnetic waves travel at the speed of light, which is extremely fast. Turns out it's the fastest thing that possible in the universe. And but again, all the things that we've developed, the fact that the wave speed is equal to lambda times f, and the displacement is equal to a sine kx minus omega t plus phi naught. This sort of description of waves we can apply to light waves and different types of electromagnetic waves. Much like with sound, though, just because we can't detect it with our bodies, with our eyes, does not mean that those types of waves don't exist. Turns out human, eyes are sensitive to light with a wavelength in about that region. You've seen rainbows before. That's essentially just light spanning that visible range. But the wavelengths of light can go from football fields, really long wavelengths, all the way up to X-rays and that with extremely short wavelengths and different energies. And again, we use these sorts of electromagnetic radiation for various different things, from microwaves to radios to X-rays. It's hard to overemphasize how much we know about just the universe and things work from just being able to measure these types of waves. But rather than go off on that tangent, all I want to stress is all these types of waves we can describe with the wave model we've built up. One final thing, I guess, I also want to stress here is we've been doing this sort of one-dimensional description where, let's look at that wave on a string again, and we have some sinusoidal wave that we've shaken, and that wave's just traveling in x and it's and time, and we describe that with d as a function of x. You're probably aware that, though, if I put a speaker, say, in the middle of a room and play it, that wave doesn't just travel in one direction. It radiates everywhere out from that source in all sort of directions away from it. And it turns out it's not really that hard to adapt our model to this. The only real difference is we can visualize it in different ways. Up till now, we've been describing these waves or visualizing these waves with these sort of drawn pictures, snapshot graphs of that wave. What we can do in this sort of two-dimensional diagram is just draw lines for wherever the crests of those waves are, and they're separated by one wavelength, and those waves or those crests end up appearing as lines on this, but you can still get the same sort of information from those images where rather the wavelength is the distance between those crests, and on these images that's just the distance between adjacent lines. And this is going to be really useful as we go on, because we're going to start to describe more realistic situations where we might have multiple sources and multiple waves, and we want to know how they interact with each other. One other thing we can do is, if you look at it, that is a common thing that happens a lot, is if you think of a speaker here and you're on the other, really far from that speaker, other side of a room, say, by the time these waves travel outwards and get there, that circle, that was really poorly drawn, but the circles are going to be extremely large and shaped that way. And if you look at, you know, if you're standing over here, to you, those waves are essentially just parallel straight lines like this. As you get further from the source, these circular sort of wave fronts become uh, parallel lines and look just like plane waves, where those crests are defining straight lines or planes in space where they have a crest, they're a high amplitude displacement. Um, so essentially, this is how we get plane waves. You put a source of a wave far from where you're detecting it, and far from that source, we essentially have planes of constant phase, we would say, but where the amplitudes are all or the displacements rather, are the same. And those planes just move through space in the exact same way we would describe our one-dimensional waves that we've been doing, where the displacement is a sine kx minus omega t plus phi naught. But anyway, again, uh, the sort of point I'm stressing here is that the wave model we built up in the last video and recapped at the start of this video can describe all the types of waves we're concerned with. You know, waves on a string, water waves, light waves, sound waves, all the things, all the types of waves we're going to deal with um, are applicable with this model, even if we move it into, you know, beyond one-dimensional waves. Again, we're going to be working on this a lot in our synchronous sessions and getting comfortable with it. If you have questions, email me and bring them to those synchronous sessions so we can discuss them.